Okay, so one example of a multi-step synthesis problem is not good enough. Two examples are not good enough. So let's look at a third. So here we've got a cyclohexane ring with a triple bond, an alkyne hanging off of it. And then what we want is a set of general reagents that we can possibly use in order to get to this cyclohexane ring that has the triple bond removed and that has an OH group on instead. So we're making an alcohol, and we've got to figure out what kind of reagent set can we use in order to get this accomplished. So over here to the side, I'm just going to kind of write down some highlights, some things that I need to keep in mind as I go forward with this whole synthesis step. And first, I've got to get rid of the triple bond. I know that there's no triple bond in this molecule. I've got to get rid of it. Well, that probably also means that if I get rid of a triple bond, then at the same time I'm also going to have to get rid of a double bond, because there's no double bond involved in this molecule either. So once I get rid of the triple, it'll probably go to a double. When the double happens, I've got to get rid of it. And then number three, I'm going to have to add on an OH group. I'm going to have to add on some type of alcohol group. However, look at the position of the OH group here. The OH group is at the end of the carbon chain. So I'm going to put that in parentheses. It's at the end, which means a terminal alcohol. And there's really only one way that we can put the OH group at the end of a molecule. And I think you kind of know what I'm hinting at, and what I'm after is that this OH group has a particular reaction that we're going to have to pick this time around, and this is a BH3THF set. So BH3THF with a little bit of hydroxide, a little bit of water, and a little bit of peroxide will allow this OH group to go onto the end of the molecule. Now, if I take a look at everything else, I don't really have to elongate. Right, this is a 2-carbon chain, and I've ended up with a 2-carbon chain. So that's why I didn't do that as a number 1 over here. I don't have to elongate any carbon chain. I don't have to add any kind of carbons onto this molecule. So for that reason, we can just go straight to that triple bond, figure out how to get rid of it, and then go from that point. Again, there's more than one possibility here, but let's just take a look at the organic and kind of talk through it. So here we've got an alkyne, and the first thing that I have to do, well, I was going to write down sodium amide, but that's for chain elongation. So we don't need sodium amide here. That is for a chain elongation step, and that is not what we're after. But what we do want to do is break this triple bond down at least to a double. I'm more comfortable working with alkenes than I am working with alkynes. So let's just go ahead and take this triple bond and break it to a double, and we do that by using H2 and Lindlar. So that way I'll end up with a 6-membered ring, and instead of a triple bond, now we've got a double bond, and hydrogen has went on to each carbon. So a hydrogen has went on to the left one, and a hydrogen has went on to the right one. So H2 and Lindlar gave me an alkene. Okay, now I can take that alkene and I can turn around and react it with my whole slew of BH3THF, OH, H2O, and H2O2, and that puts a alcohol group onto a double bond. So I'm just going to rewrite this structure over. My double bond has been targeted. It has broken down to a single. 2 sites of attachment have opened up, and H and OH will go on to those sites. Well, traditionally H would go on the right hand side here because that's where the other hydrogens are located. But this makes it go backward, and that's what we need. So the hydrogen will go here to the left, and OH would go there to the right. And I can rewrite this structure if I want to kind of make it look like the product. So this CH and the H hanging off turns into a CH2, and that's connected to another CH2, and that is connected to an OH. So here we finally have our product. Now, did I have to use H2 and Lindlar first? And the answer is no. You could have, if you wanted, taken the triple bond and you could have added the BH3, THF, OH, H2O, H2O2 if you have wanted to do that route to put the OH group on the end with this double bond. However, if you would have done that, you would have ended up with an enol. So let's come down here below and let's take a look at that structure maybe on how that would have been a little bit different. So we could have maybe wanted to do this route, take my alkyne and add my BH3THF, or my alkylated boron that we talked about in a couple of videos previously. And I could have done this number, and this triple bond would have been broken down to a double. So here's the starting reagent that would have been broken to a double, and two sites of attachment would have opened up. This would have added my OH group on the opposite position because it's still anti-Makovnikov, and hydrogen would have went here. And you might want to have done that, and then you would probably wanted to add H2 and platinum in order to change this double bond down to a single bond. But the problem is this is a no. You don't want to do this first, because if I take a look at this functional group that I have created, this is an enol, and this enol will rearrange on me. So if I do choose this route, and it looks like a possibility in the very beginning, but if I choose this route, what would happen is that this molecule would rearrange before I had a chance to actually go in and add my other reagent on to break that double bond to a single. So what would happen is that this molecule would rearrange, this would change into a single, this hydrogen would disappear, and what we would have would be a double bond and another hydrogen that shows up here. So we would have ended up with a aldehyde, CH2, C double bond OH. And this is not the product that we need, because this is the aldehyde form, and what we want from the very beginning up here is the alcohol form. So traditionally, it looks like that would have worked. However, you've got to be really careful, especially when these enols form in the presence of the alcohols, because when those enols form, they will rearrange automatically before you get a chance to hit it with the second round of the multisynthesis step. So that's something that you've got to watch out for every single time. So let's do another quick example if we can, and this time let's take a look at carbon, triple bond carbon, and we want to know what has to happen in order for me to get CH3, CH2, and I'm going to show a little bit of stereochemistry this time just to play that off, and we get this form here. This is a E form. My hydrogens are on opposite sides, so this could be trans or E depending on how you want to name it, and this is 2-pentene. So we want to go from this C triple bond carbon to this structure, which is E2-pentene. First off, I'm going to come over to the side and write down really what I have to think about doing as far as the synthesis goes. So 2 carbons, and I'm going to end up with a 1, 2, 3, 4, 5 carbon chain. So I'm going to have to elongate. I know that at least. I'm going to have to elongate that carbon chain in some form, in some fashion. Number 2, I start off with a triple bond, so I'm going to have to get rid of that triple bond. When I do, that takes me to a double bond. And that's good because this molecule has a double bond there. And number 3, when I go to a double bond, I have to keep stereochemistry in the front of my mind because I'm drawing it in a specific way. I specifically put E there. So I'm going to have to think of how on earth can I get an E molecule to take place. So we've talked about those general reagent setups, and in the next video we'll go through and we'll work through the proper reagent order in order to get this product.